In the last video we saw that the only difference between DFA and NFA is in NFA, instead of a single next state, you get a set of next state depending on the current state and the current symbol, right? So that is why the signature is this. You take a current state and current symbol and it gives you a set of next state here, right? So it is a single step process, and then we defined the extended transition function which takes care of strings here. So instead of sigma here we will have sigma star, and that we defined like this. So you start from a state, and this should be such that it takes a string and it again gives you a set of states, which is here. So here and we formally wrote this thing, so it all depends on this argument. So we formally defined the delta hat as this using these equations. So again, this is a function which takes a single state and a string and then gives you a set of states, right? The states that it can reach on this string starting from this state. Now let us generalize things a little bit. So we have considered this transition function for NFA, which takes a single state. Sorry. So it's transition function for NFA which takes a single state, and depending on the current symbol it gives you a set of states. Okay, so now we want to generalize this part. So instead of a single current state, we consider a set of current states. Okay, let's call this capital A, and then we ask what are the set of next states. Okay, so we want to define something like this. So this is a set of current states. We take a symbol and then we ask what is the set of next states. So the signature will be like this. So this is the power set of Q, this sigma, and again this is the power set of Q. So the signature should look like this. And how do we define this mathematically? So it's simple. So you take the sets for each of this pi here in this capital A, and you take their union, right? So this is the equation that we are talking about. So it comes from this, if you think of this picture. So these are the set of current state, and these are all the possible next states on symbol A, right? This is how we define it. So once we have this, we can also think of this sort of multiple transition. So for NFA, in fact, with a single current state, it was precisely the extended transition function delta hat, right? So which takes the current state and which takes then a string, so this string W, and then it gives you the set of states that you can reach by processing this string W starting from this state Q, right? So we can sort of consider the similar possibility, but instead of a single starting state or single current state, we now consider a set of current state. So now how do we compute this thing? So instead of writing equation, so let us just consider this picture. So now as I said, so suppose you are given this NFA, say take this NFA, and then how did we define this delta prime? So instead of considering a single current state, we are considering a set of current states, and then again on symbols we are looking on what are the possible next states. So this will come directly from the transition function delta itself, because these are singleton states, right? First of all, if your set of current state is phi, then obviously the set of next state is also phi. So this is trivially true. This phi, right? And then for this, since these are singleton set of current states, so these are like the sets itself. So you have this table here. So this part actually is just same as this part, just that we are expressing these things as singleton sets. But now if you consider, say, this set of current states, so now instead of just a single current state, we are considering the possibility that we could be in 0 or we could be in Q1. And if that is the case, and now if suppose we take this input symbol 1, then what can happen? So if you are here or here, so if you are here on receiving 1, you should take this transition and you will come back to this Q0, right? But if you are here on taking 1, you will move to this state, right? So your set of next states will be Q0 and Q2. So this is what this is Q0, Q0, Q2, right? So in this way you can prepare this table for all subsets of Q, right? So this is a function from 2 to the Q times sigma to 2 to the Q. Now if we just take this 2 to the Q as Q prime, just define it. So then it looks like this Q prime times sigma goes to Q prime. Now if you just look at this function, this looks exactly like a transition function of a DFA. We haven't defined the DFA yet, but this looks like a transition function of DFA. Why? Because for DFA this and this was same, right? Now you may say that yeah, this is not a single state, this is a set of state, this is a set of state. But look at this diagram that we get from this table. We can express this transitions as this graph, right, again. So though each box is a set of states, but we can treat them as some kind of single identity, right? So this looks like states of some kind of DFA, and this is a DFA because this function is from Q prime to Q prime, right? And so if we take Q prime to be the set of states, so now what are the set of states? The set of states is the power set of the state that you had for this NFA, right? So a state here corresponds to a subset of Q here. So in that sense we get a DFA. So important thing is that this is a DFA because of this, and we have the transitions, right? So now if you follow multiple transitions, for example, if you follow, say, this transition on 0, and then from here if you follow this transition on 1, so what does that tell you? So it tells you that if you start with this set of current states, so this set of current states means here it's singleton, so that means you are starting with just Q0, right? So then on receiving 0, the next set of states are this, right? And if, and this is visible from here, so if you take this path, then you are in Q0. If you take this path, you are in Q1. So this will be Q0, Q1. This is also reflected here, and this is also reflected here also. So then from here, if you take 1, so as we mentioned, you get there, right? So that means this state gives you the set of possible states which you can get to by processing the string 0, 1. So by processing 0, 1, so consider this as your input string, and then you are starting from say state q0, and then in the NFA it looks like you can go to either q0 or q2, right? So what is happening here is, this is in fact a DFA, and what is the set of states? So the set of states is this 2 to the q. The transition function is this delta prime, and this is true. So this red box here. So in our NFA, we have a path, say from state q to p, if and only if, so this is important, if and only if we have a path here from say this singleton set. So now this set itself is a state in our DFA. So if we have a path from here, so this current state to some other state, again here you can get only one set, right, because this is a DFA and this is the signature. So we can get to a set where which includes this p, right? There can be other states, but this includes this p. And what are these other states? So these are precisely the states that you can reach from here. So suppose you can reach say some p prime, say p double prime here. So all this p prime, p double prime, so they will also be there. But the point is, if you have any path from say q to p on input string w in the NFA, okay, in the NFA, so here I have this NFA. So this happens if and only if you have a path. So now this path is unique and this result is also unique. Result means the set as a result, starting from a set also. So yeah, you have this path where this thing contains p, right? Because this thing is precisely the set of all states that you can reach on input w in the NFA, right? So with this you can easily see that we can consider this DFA. So this, as I said, this will be starting state. So so this is the DFA that we are defining. This is the starting state, this is the set of state, and this is transition function. And then now how can we define the set of final states? See, now you see that this DFA kind of emulates or simulates this NFA, right? Now if we want to ensure that whatever string is accepted here is also accepted here, then what do we need to do? So what was the acceptance condition for NFA? So it was discussed in the previous video. A string in this NFA is accepted if there is a path from q0 to q2 on this string, right? So there can be many paths, many paths. Some of those paths will reach this q2, some of those paths will reach this non-final states, q0 or q1, right? But if any one of that path reaches this q2, so then that string is accepted, right? And how do we express the fact in this picture that whatever path we have for say input string w, so out of all the possible q1 reaches this q2. So say so we can make all the states final states which contains q2, right? So as we saw on 0 0 it can reach either q0 or q2, but if it can reach q2 then we know that sorry, on 0 1. So if it reaches q2 on 0 1, so that's fine. That means this 0 1 is accepted in our NFA. So here also we can make this final state. So here since this is the only final state here, so here the logical thing is to define those final states such that this q2 is included. So this is a final state, this is a final state, this is a final state, and others are not. And one thing I think have already noticed that since this is our starting state and following the arrows from here, you can only remain in this part, because this part is actually completely disconnected from the other part, right? So this part is completely disconnected. So even if you remove this thing, it's fine. So you will get a DFA with this 4 states, right? And that will be a equivalent DFA for this NFA. Now this is a particular example, but this is general enough. So you got this idea, right? How to construct a DFA. So what are we doing? So this is the formal construction. So this NFA is given, right? This NFA n is given with some set of state, some transition function, some set of final states. So the first thing we did was we defined a DFA with the set of states, where this set of states in the DFA is actually the power set of this Q here, right? So now a state here means a subset of states here, right? And then the starting state is this singleton set Q0. We cannot just put Q0 here because here things are subsets of Q. So it starts with Q0 means it starts with the singleton set Q0, right? And then we defined this transition function using this, right? So this is what we got. So we use this same definition for a general construction. So yeah, here is the construction, sorry, definition. And what are the final states? So you remember we define the final states. So what are the states here? So the states here again are subsets of states here, right? And we included all those subsets which contains a final state, which is a final state here, NFA. So if this is, say, corresponds to this Fn, so we want to make all those A's, say A is some subset of Q, so we want all those A's to be final state in the DFA which contains some set in Fn, right? Okay. So if you feel comfortable, just go back and forth and just match that this is the condition that captures that idea. Okay. So and then you show that they accept the same language by showing a slightly general statement that their transition function is kind of essentially same. So what I mean by essentially same, so this starts from Q, this state Q, and this is for the non-deterministic thing, right? So it starts from Q, where this Q belongs to this capital Q, right? And then if it processes this string W, then it goes to some set of states, right? And we showed that this is the same set of states that you also get by processing W starting from this Q. So again, here Q is just singleton set Q. And this is the hatted version, because here we are using string, right? So this we can show for any state Q and any string W. And how does that imply this? Just a special case if we put Q0, this Q0 here, right? So this will be a starting state here, this will be a starting state here, and we need to show that so the acceptance condition for DFA was this, if you remember, right? So this thing must be in one of the final state. So that was for DFA, right? And for NFA, the acceptance condition was that this thing must contain some final state. So these are from the definition of DFA and NFA. If you forgot, then just go back to the definition of DFA and definition how we defined acceptance criteria for DFA and NFA formally. So you just go back to those equations and see that these are precisely the equations for acceptance criteria for DFA and NFA. So this if and only follows from this equality, right? And how do you prove this equality? Just by using induction. Again, it's trivial. It almost requires no proof, but again, at least for some initial classes, I'll try to write down the formal proofs with all their details, because you should see how it looks like. You should be able to do it yourself, but still. So base case is the string has length 0, so induction on length of this W, and then by definition of this hat function, again, if you forgot, you go to those definitions. What it says that what is this hat? It takes a current state and it takes a string and it gives you the next set of states, right? So if you are not processing any string, then you remain in this thing, the same thing. So this is what it is, and again from hatted version here also you get this. So this is trivially true. And then on induction step, you break this into, say, XA, where this X is so this X is a string. So this X belongs to sigma star, and this A is just a symbol, right? So A belongs to just sigma. So if you do this, then again, this is a fairly simple thing. Everything follows from the equations that we wrote, right? So this follows from the definition of delta hat for DFA. If you see the definition of delta hat for DFA, so this equality follows from there. So this is exactly how we define these things. And then here this D is converted to N. So we convert this transition function of this deterministic automata to non-deterministic by our induction hypothesis, right? So this is the thing that we are trying to prove for W, but this X is smaller than W. So by induction hypothesis, this is already true for X. And then again, this follows from the definition of this delta D that we defined here, right? So from this definition itself, it follows from here to here. And then by definition of delta hat of N, again, if you just go back and look into the definition of delta hat of non-deterministic finite automata, it follows that this is equal to this. So so as we progress, I won't go through this proof. So it's enough to just mention this, that use induction on the length of input string to show this. So maybe I'll just write this one line, and I expect you to fill up all this boring and obvious details, right? So this theorem proves that given any NFA, you can construct equivalent DFA. In the previous class, we proved that given any DFA, you can construct equivalent NFA. In fact, the DFA is a NFA. So together, it proves that NFAs and DFAs are equivalent. So for finite automata, determinism and non-determinism are equivalent. So later we will consider a slightly different kind of non-determinism using something called epsilon transition. So again we will show that even with that kind of non-determinism, that model will be equivalent to this NFA or DFA. So everything is equivalent. So that will be our next topic. So NFA with epsilon transition. But for now, at least we know that these two versions are equivalent.